Have you ever wondered what holds us to the Earth, what makes the moon orbit our planet, or what guides the planets around the sun? The answer lies in a fundamental force of nature: gravity. Gravity is the invisible force that attracts any two objects with mass towards each other. It's a universal attraction, affecting everything in the cosmos, from the smallest particles to the largest galaxies. Imagine throwing a ball into the air. It goes up, slows down, and then falls back down. This familiar phenomenon is due to Earth's gravity pulling the ball back towards its center. The more massive an object, the stronger its gravitational pull. That's why we feel Earth's gravity much more strongly than the moon's, even though the moon is also pulling on us. Gravity isn't just about pulling things down, though. It's the cosmic architect, shaping the universe on a grand scale. It's the force that brought together the matter that formed our planet billions of years ago. It's the reason why the moon orbits the Earth, and why the Earth and all the other planets orbit the sun. Without gravity, our universe would be a very different place. There would be no stars, no planets, and no galaxies. Instead, matter would be scattered randomly throughout space. Gravity is the invisible glue that holds everything together and gives the universe its structure. Sir Isaac Newton, a brilliant physicist and mathematician, revolutionized our understanding of gravity in the 17th century. He formulated the law of universal gravitation, a simple yet profound equation that describes the force of attraction between any two objects. This law states that every object in the universe attracts every other object with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Let's break this down with a simple example. Imagine two apples, each with a mass of 1 kilogram. If you hold them a meter apart, they will attract each other with a very tiny force. This force is so small that you won't feel it. But if you could somehow increase the mass of one of the apples to the mass of the Earth, the force of attraction would become much stronger. In fact, it would be strong enough to make the other apple fall towards it, just like objects fall towards the Earth. Newton's law tells us that the more massive the objects, the stronger the gravitational attraction between them. It also tells us that the closer the objects are, the stronger the attraction. That's why the moon, which is much closer to Earth than the sun, has a greater gravitational influence on our tides than the sun, even though the sun is much more massive than the moon. Newton's law of universal gravitation was a groundbreaking discovery. It provided a mathematical framework to explain the motion of celestial objects, from the falling apple to the orbits of planets. It was a testament to the power of human ingenuity to decipher the laws of nature. Imagine a bowling ball placed on a trampoline. The ball creates a dip in the trampoline surface. Now, if you roll a marble across the trampoline, its path will curve as it passes near the bowling ball. The marble is affected by the dip created by the bowling ball, even if they don't touch. This is a simple analogy to understand the concept of a gravitational field. A massive object like the Earth creates an invisible field around it that extends throughout space. This field is a region where other objects with mass experience a force of attraction. The strength of the field decreases as you move further away from the object, just like the dip in the trampoline becomes less pronounced further away from the bowling ball. The Earth's gravitational field is what keeps us grounded. It's why objects fall towards the Earth when dropped. It's also why the moon orbits our planet. The moon is constantly being pulled towards the Earth by its gravitational field, but its own forward motion keeps it from crashing into us. The concept of a gravitational field helps us visualize gravity's influence across vast distances. It's a useful tool for understanding how stars and planets interact within galaxies and how galaxies themselves cluster together in the universe. Section 4. The pull of our planet. Understanding acceleration due to gravity. We've all experienced the pull of gravity in our daily lives. When we jump, we always come back down. When we drop something, it falls to the ground. This constant pull towards the Earth's center is what we call acceleration due to gravity. Imagine standing at the top of a tall building and dropping a tennis ball. As the ball falls, it picks up speed at a constant rate. This rate of increase in speed is the acceleration due to gravity, which is approximately 9.8 meters per second squared on Earth. This means that for every second an object falls freely, its speed increases by 9.8 meters per second. Now imagine dropping a feather and a bowling ball simultaneously from the same height in a vacuum, where there's no air resistance. Surprisingly, they would both fall at the same rate and hit the ground at the same time. This is because the acceleration due to gravity is constant for all objects near the Earth's surface regardless of their mass. This concept might seem counterintuitive at first, as we instinctively associate heavier objects with faster falling. However, the reason a feather falls slower than a bowling ball in everyday life is due to air resistance, not a difference in gravitational pull. In a vacuum where air resistance is absent, both objects experience the same acceleration due to gravity. Section 5. Define gravity, exploring free fall and weightlessness.